Here are your solutions to homework number 1. My apologies in advance. We're going to have to run through these pretty quickly, about 8 problems in less than 20 minutes, so my explanations will be a little bit sparse. But feel free also to use the YouTube tools to slow this down to half speed if it will help you to understand better. You can also download a PDF copy of these solutions from Blackboard. So in question number 1, you're given a linear transformation defined by multiplication by this matrix, and then asked a few questions about the nature of that transformation. First of all, what is the dimension of the domain of the transformation this matrix defines? Well, because this matrix has 3 rows and 4 columns, that means this matrix can multiply vectors on the left if those vectors are 4 by 1. In other words, if they live in R4. And when it does so, it produces vectors that are 3 by 1. In other words, they live in R3. So, if x belongs to R4, then AX belongs to R3, and therefore this matrix defines a linear transformation from 4-dimensional space into a 3-dimensional space. To find a basis of the column space of A, we just need to find the pivot columns of A. We can find the pivot columns of A by row reducing the matrix A enough to be able to locate where its pivots are. We can row reduce this particular matrix by subtracting the first row from the third in order to kill the one in the lower left, and then subtracting the second row from the third to kill the one that's in the leading position on the bottom row. We find that the first 2 columns of A are pivot columns, and therefore a basis for the column space of A consists of the first 2 columns of A, 1, 0, 1, and minus 1, 1, 0. To find a basis for the null space of A, we need to solve the system AX is equal to 0. Luckily, if we set up the augmented matrix for this system, we've already done the row reduction steps in the previous problem in order to solve this system, so we can skip straight to the row reduced version and the zeros won't change on the right hand side. Because we had 2 pivots, we have 2 bound variables in this system. We also have 2 free variables. If we assign those free variables names s and t, then the system that we get if we write it back in variables looks like this, where x3 is equal to s and x4 is equal to t. And writing this in parametric vector form, we find that x3 is equal to s, x4 is equal to t, and therefore if we break out the s's and t's, we'll get a 1, 0 and a 0, 1 in the third and fourth positions respectively. And then solving the equation for x2, we find x2 is equal to minus s plus t, which gives us minus 1 and 1 in those positions. And then solving the resulting system for x1 gives us x1 is equal to minus s. And therefore a basis for the null space consists of these 2 vectors, minus 1, 1, 0, and 0, 1, 0, 1. So, in conclusion, can we say that the vectors that belong to the null space of A are orthogonal to the rows of A, or are they orthogonal to the columns of A? Well, they're orthogonal to the rows of A by the nature of matrix multiplication. And to check this for this particular matrix, you can check that, for example, the first row of A multiplied in the sense of taking its transpose and then multiplying by the column vector minus 1, 1, 0, which was in the null space of A, you can check that that product is equal to 0, and therefore that first row of A is orthogonal to that first basis vector that we found in part C. And you can check the others as well. For question 2, you're given a subspace of R3, which consists of vectors whose first 2 components are equal. For example, this might be the plane with the equation x is equal to y inside of R3. And you're supposed to find 2 different bases for this particular subspace. One way of finding a basis for this subspace is to think of the equation which defines our subspace x equals y as an underdetermined linear system. If we think of it as an underdetermined linear system, we can use linear algebra tools to solve that system and describe it in parametric form. To do that, we just need to row reduce this augmented matrix, and there's no row reduction to be done because there's only 1 row. The x is a bound variable, but that means that y and z are free, so we'll give them parameter names s and t, and thereby obtain the equation x minus s is equal to 0, y is equal to s, z is equal to t. Factoring out the s's and t's, we obtain a parametric vector form for this solution, s times the vector 1, 1, 0, and t times the vector 0, 0, 1, and therefore a basis for this subspace, which is the solution space of x minus y is equal to 0, consists of the vectors 1, 1, 0, and 0, 0, 1. To find a second basis, we can use this first basis. In order to use the first basis, we can just take any linear combinations that we like of our original basis vectors, and as long as the 2 linear combinations that we choose are independent of one another, we're going to get a new basis for the same subspace. So for example, if I multiply the first basis vector by 1 and the second basis vector by 1 and I add them together, I get a new basis vector 1, 1, 1, which still belongs to the same subspace as the original basis vectors did. If I then take an independent combination, say -3 of the first plus 2 of the second, I get another basis vector -3, 2, which also belongs to the same subspace and which is linearly independent of our 1, 1, 1. So I get a new basis here. Your answers might vary because you might choose some different combinations of basis vectors here. In question 3, we're asked to show that it's impossible for a vector to be perpendicular to everything in Rn unless that vector is itself the zero vector. So here's how we can prove that. Let's take x, which is an arbitrary vector in Rn, and let's actually write out its components, x1, x2, up through xn. These are scalars, x is a vector. So what do we know? We know that if I pick any vector at all y, that x transpose times y is going to be 0. So in particular, let's suppose that we choose y to be the first coordinate vector, the first standard basis vector in Rn, 1, 0, 0, 0, etc. up to 0. Then, because we know by assumption that for all y in Rn, x transpose y is equal to 0, that means that x transpose times this y must be equal to 0. But x transpose times this y, if we do it out, is x1 times 1 plus x2 times 0 plus and so on up to xn times 0, which is just going to give me x1. And therefore, x1, the first component of our arbitrary vector x, must be equal to 0. But there was, of course, nothing special about us choosing the first component in this example. We could as well have chosen the second, the third, all the way up to the nth. So we can run the same argument again, just with an arbitrary standard basis vector, ek. So for any k between 1 and n, so for any of our coordinate vectors, if we choose y to be the kth standard basis vector with a 1 in the kth entry and a 0 everywhere else, then because by assumption x transpose y was equal to 0 for all y, and we do out the arithmetic, x transpose times ek is going to give me just xk, the kth entry of x. Therefore, the kth entry of x is equal to 0. And because this was true for all k from 1 to n, that means that every one of the entries of x must be equal to 0, and therefore x must be the 0 vector. So the upshot of this argument is that it's impossible in n-dimensional space to have a vector which is orthogonal to everything unless that vector is the 0 vector. In problem 4, you're asked to determine projection matrices. In one example, projection matrix in R2. In the second and third examples, they're projection matrices in R3, and projections onto subspaces that are given to you. In the first example, we'll do it with a line. In the second and third examples, we'll do it with a plane. The main element for this construction is the projection matrix formula. P is equal to A times the inverse of A transpose A times A transpose, where A is a matrix whose column space is the subspace onto which we're projecting. So to project points onto the line y equals 2/3 x, which looks like this in the xy plane, what we need is a basis for that line. Since it's a one-dimensional subspace, we just need a single vector which belongs to that line. And I'm going to choose one that has integer coefficients just to make my life easy. I can choose the vector 3, 2, and then that will be my matrix A. Then to find the projection matrix P, we just need to run through the projection matrix formula. A times the inverse of A transpose A times A transpose. And doing out that arithmetic, we have 3, 2 times 3, 2 as a row times 3, 2 as a column, quantity inverse times 3, 2. We'll process the quantity in parentheses first and then take its inverse. A transpose A gives me the 1 by 1 matrix 13, whose inverse is going to be the 1 by 1 matrix 1 over 13. And then running 3, 2 times 3, 2, the column times the row, gives me the matrix 9, 6, 6, 4. And so the projection matrix we want is 1 over 13 times the 2 by 2 matrix 9, 6, 6, 4. To do this in a higher dimensional example, where we're projecting R3 onto a hyperspace, a two-dimensional plane in R3 in part B, we can start by using the vectors that we were given as a basis for our plane. And the reason we know that V and W form a basis for this plane is because they're linearly independent and our plane is two-dimensional. So we can take, for our matrix A, the matrix whose columns are V and W, -1, 0, 1, and 1, 1, 1. Then we just again need to turn the crank on our projection matrix formula, A times the inverse of A transpose A times A transpose, and here there's a lot more sort of nasty linear algebra to do. It's not too bad, it's just kind of tedious. The quantity in parentheses, if we multiply it out, gives me 2, 0, 0, 3. It's a 2 by 2 matrix. We need to find its inverse. Well, luckily the gods have smiled upon us, and that matrix is diagonal, and so its inverse is just the reciprocals of the numbers on the diagonal, which if I factor out a 1/6, I can call it 1/6 times 3, 0, 0, 2, just to keep everything integers. And then to do the rest of the matrix multiplication, we'll multiply 3, 0, 0, 2 by the A transpose matrix, which operates on multiplication by the rows, so minus 3, 0, 3, 2, 2, 2. And then the multiplication of the red matrix by the purple matrix here will give me a 3 by 3 with entries 5, 2, minus 1, 2, 2, 2, minus 1, 2, 5. That multiplied by 1/6 is the projection matrix that we're looking for. In the last example, we're given a plane onto which to project, but we're not given a basis for that plane, so our first job is going to have to be to find one. To find a basis for the plane which is described by the equation 2x minus y minus z is equal to 0, we'll again treat it like it's an underspecified linear system, x being a bound variable, y and z being free variables. And so if we set y and z equal to parameters s and t, then we can express s in terms of those parameters. X equals 1/2 s plus 1/2 t, just solving the equation for x. And then factoring out the s and the t, we can find basis vectors, namely 1/2, 1, 0, and 1/2, 0, 1, that describe our plane. But I don't like fractions in this example, so I'm going to take those basis vectors and clear denominators, multiplying each of them by 2, to give me 1, 2, 0, and 1, 0, 2 as basis vectors for my plane, and therefore the columns of the matrix A for our projection formula. And then we just have to turn the crank on the projection formula one more time. A times the inverse of A transpose A times A transpose. A transpose A in this example gives me 5, 1, 1, 5. I can invert that matrix using the quick 2 by 2 inversion formula, multiply it by the blue matrix on the right, multiply the result by the red matrix, and I'm going to end up here in this example skipping over all the computations with 1/6 times the matrix 2, 2, 2, 2, 5 minus 1, and 2 minus 1, 5. This is a purely computational problem, but probably the trickiest step is just getting started, finding out your matrix A, whose columns form a basis for the subspace onto which you're projecting. Question 5 asks you to find an example of a non-zero vector in 3 space, which is orthogonal to a given pair of vectors v and w. Here those vectors are minus 2, 1, 3, and 1, 0, 1. Well, from vector calculus, we know that there's a quick way to do this because we're in 3-dimensional space. The quick way to find a vector which is orthogonal perpendicular to a pair of vectors is to compute the cross product of those two vectors, v cross w. That will be orthogonal to v, and it will be orthogonal to w. Computationally, there are a number of ways to remember how to compute a cross product. The one that I like is to set it up as the 3 by 3 determinant with v and w on the second and third rows, and the first row containing the standard basis vectors e1, e2, and e3. And if I take this 3 by 3 determinant, the first entry is going to be 1. 1 times 1 minus 3 times 0 times e1. The second is going to be 3 times 1 minus negative 2 times 1 times e2, so that gives me a 5 in the 2 slot. And then the last is negative 2 times 0 minus 1 times 1, negative 1 in the e3 slot. So computing the cross product of v with w is a quick way of answering this problem, but it only works because we're in 3 dimensions. Cross products don't exist in other dimensions besides, well, there's a weird one in dimension 7, but we don't care about that one. So in order to generalize this, which is what we're asked to do next, we should probably look at how we could do this the longer way. What's the more general way of finding a vector which is orthogonal to a pair of given vectors? So if my unknown vector has coordinates x, y, z, then if we want it to be orthogonal to v, then we need x transpose v to be equal to 0. If we want it to be orthogonal to w, we need x transpose w equals 0. And what that does is it gives me a system of 2 linear equations. X transpose v is going to be negative 2x plus y plus 3z. That's got to be 0. X transpose w will give me 1x plus 0y plus 1z. That has to be 0. And solving this, again, underspecified linear system can give me the vector that I'm looking for. So I'll augment this matrix and row reduce it to the extent that I can. I'll clear out that second row. I row reduce it, I find that I have a single free variable, so I have a one-dimensional solution space. X and y are bound variables in this example, so we'll let z equal t. And then going through and solving for x and y in terms of t will show me what my parametric vector form for this solution is. X is equal to minus t, y is equal to minus 5t, z is equal to t. Factoring out the t, we can find that a basis for our solution space is the vector -1, -5, 1. And so any multiple of that vector will give me a vector which is orthogonal to both v and w. For example, if I pick t equal to -1, I get exactly the vector that we found when we took the cross product, 1, 5, -1. If I choose a different value for t, I'm also going to get another vector which is orthogonal to v and w. So if I choose t equals 4, for example, I get a different vector that will also work to solve this problem. And because the cross product existed in R3, there was a quick way to do this. But if we go up into R4, we no longer have a cross product, but this linear algebraic way will still work. So in the four-dimensional scenario, we would just have an additional coordinate, say x, y, z, w, in our unknown vector, and that coordinate will end up being a free variable in our solution, so we'll have a two-dimensional space of solutions to work with in the case where we do this in R4. So in other words, we'll have kind of a whole plane worth of possible answers, whereas when we do this in R3, we only get a line's worth of possible answers, which can, if we just pick a single vector on that, can be computed with a cross product. Problem 6 asks you to prove the so-called rhombus identity, that if I have two vectors in Rn, then their sum is orthogonal to their difference, x plus y orthogonal to x minus y, if and only if the norm, the magnitude of x, is equal to the norm of y. So I'm going to begin by sketching the picture. If I have two vectors x and y, then by definition of sort of Euclidean vector addition, if I take x plus y, what I get is a diagonal, the long diagonal in this example, of the parallelogram whose sides are x and y. Likewise, if I take x minus y, I get a vector which points from y to x, and so we can consider that to be the other diagonal of this parallelogram. And in this particular example, if we measure the angle in between those two diagonals, we see that, if this drawing is to scale, those diagonals are not necessarily perpendicular in a general case where x and y have no relationship. The diagonals of this parallelogram bisect one another, but they don't do so at a right angle necessarily. But if x and y have the same length, then instead of a parallelogram, we get the more special figure called a rhombus. So the length of x is equal to the length of y. And in this case, if we construct the diagonals x plus y and x minus y, we should see that they form a right angle. So how do we prove this? Well, what we're really trying to do is measure the angle in between these diagonals. In order to measure the angle in between x plus y and x minus y, what we really need to do is take the dot product, compute the dot product of those two vectors, which in the language of our course we write as the transpose of the first multiplied by the second. Well, luckily, matrix multiplication is distributive over addition, and so we can FOIL out this product into x transpose x minus x transpose y plus y transpose x minus y transpose y. Now, the dot product of vectors is a commutative operation. It's a symmetric operation. So x transpose y and y transpose x are the same thing. They give you the same result. So we can trade out the y transpose x for another x transpose y in this expansion and cancel out the second term with the third. So we get x transpose x minus y transpose y. But now remember, what is x transpose x? X transpose x is nothing more than the square of the norm, the magnitude, of x. So we can rewrite x transpose x as the square of the norm of x, y transpose y is the square of the norm of y. So the dot product of these two diagonals is nothing more than the difference between the squared lengths of x and y. And that difference will be equal to 0 if and only if the norm of x and the norm of y are equal. And having that dot product be equal to 0 is by definition exactly the same as having those two vectors be orthogonal to one another, and so we have proven that x plus y will be orthogonal to x minus y if and only if the norm of x is equal to the norm of y. In question 7, you're asked to compute the angle between the diagonal subspace of Rn and the coordinate axes. The diagonal is the subspace consisting of all points whose coordinates are all equal to one another. Well, in order to find that angle, we need a basis for d. And a moment's reflection should convince you that a basis for d that we can use is the vector that consists of all 1s. Every element of d is a multiple of the vector 1, 1, 1, 1, and so on. So to find the angle that makes with the coordinate axes, let me take a vector which points in one of the coordinate directions. Let's say e1, the vector 1, 0, 0, 0, 0, 0, up to 0. If I measure the angle between those two vectors, I'll get the angle between d and, let's call it the x-axis, or the first coordinate axis. But because of symmetry, that will be the same as the angle between d and all of the other coordinate axes as well. How do we find the angle between two vectors? Well, the angle theta is going to satisfy cosine of theta is equal to the dot product of the two vectors divided by the product of those vectors' magnitudes. So v transpose E1 divided by the product of the magnitude of v and the magnitude of E1. V transpose E1 we can compute as 1 times 1 plus 1 times 0 plus 1 times 0, etc., etc. So that numerator is going to be just 1. The norm of v is going to be the square root of the sum of the squares of the entries of v, but all the entries of v are 1, and there are n of them, so we end up with the square root of n, being the norm of v. E1, of course, has norm equal to 1, because its only non-zero entry is the first entry, which is a 1. So our angle is going to satisfy cosine of theta equals 1 over the square root of n. So theta is going to be the arc cosine of 1 over the square root of n. We can compute numerically some of those values. The arc cosine of 1 over the square root of 2 is 45 degrees, showing that in 2 dimensions the diagonal makes a 45-degree angle with the coordinate axes. That you can convince yourself in the xy plane without too much difficulty. In 3 dimensions, we get the arc cosine of 1 over the square root of 3, which we'll need a calculator to approximate as about 54.74 degrees. When n is equal to 4, we get the arc cosine of 1/2, which is 60 degrees. So in 4 dimensions, the diagonal makes a 60-degree angle with the coordinate axes. As n marches up toward infinity, what happens to this angle? What is the limit of the arc cosine of 1 over radical n as n goes to infinity? Well, as n goes to infinity, 1 over radical n goes to 0. So since arc cosine is a continuous function, we can move the limit past the function and get the arc cosine of 0. And the arc cosine of 0 is 90 degrees. So the higher our dimension, the closer the angle between the diagonal and the coordinate axes becomes to being a right angle. Finally, in question 8, you're asked to complete and prove the following statement. If P is a projection matrix onto a subspace of Rn, then P is an invertible matrix if and only if something. We're going to discover what that something is. Let's start with a lemma about projection matrices. If P is a projection matrix, in other words, if P achieves projection onto the subspace S, then what is P squared going to be? What happens if I project something and then I project it again onto the same subspace? Well, projection is a lot like drying your clothes. You can't over-dry, you can't over-project. Once something is dry, it's dry. Once something is projected, it's projected. So projecting something onto a subspace twice is the same as projecting just once. P squared should be equal to P. Here's the proof. Using the projection matrix formula, P is equal to A times the inverse of A transpose A times A transpose, we can directly compute what P squared is. It's equal to P times P. And by definition, each of those P's has the projection matrix form. So we end up with this big expression. But what you'll see happens in this expression is we end up with the inverse of A transpose A multiplying A transpose A. And by the associativity of matrix multiplication, we can single out that product as the product of a matrix with its own inverse, which becomes the identity. And therefore, that factor vanishes and gives me just A times the inverse of A transpose A times A transpose, which is just P. So when we do out all the arithmetic for a projection matrix, P squared is the same thing as P. Great, so now what happens if P is in addition invertible? So given that P squared is equal to P, and that P is an invertible matrix, we can take the inverse of P and left multiply this equation on both sides by it. And if I do that, then on the left side, P inverse times P squared is P inverse times P, and the P inverse P cancels to the identity. On the right-hand side, P inverse P cancels to the identity, and so when all the dust settles, P, on the left, is equal to the identity matrix on the right. And so, if P squared is equal to P and P is invertible, that necessitates that P is the identity matrix, and that's how we'll complete the statement of this claim. And we've proven, therefore, the forward implication. If P is an invertible projection matrix, then P is the identity. But this is an if and only if statement, so we have to prove the other direction as well. Conversely, let's assume that P is the identity matrix. Then clearly P is invertible, because the identity matrix is its own inverse. But why is P a projection matrix? How do we know P is a projection matrix if P is equal to the identity? Well, choosing A equal to the identity matrix itself, the projection matrix formula will give us A times the inverse of A transpose A times A transpose is going to be I times the inverse of I transpose I times I transpose. But all of those products and inverses end up just being more I's, because I transpose I is I, and because I inverse is I, and because I times I is equal to I, then we end up with I here. So we can recover the identity matrix from the projection formula by choosing A equal to the identity matrix. So the upshot of this claim is that we cannot have an invertible projection matrix unless that projection matrix is the identity.